Hey, so if you're into physics, you've probably heard of the legendary problem book by I.E. Irodov. I mean, his problems are famous for being real brainbusters, the kind that really make you think. So today, we're going to tackle one of those classics, problem 1.22 from the kinematics section. It looks pretty innocent, but trust me, it's a brilliant workout for your physics brain. Let's dive in.
So here's our game plan. First, we'll unpack the problem itself, figure out what it's really asking. Then we'll line up the physics tools we need to solve it. After that, we'll get our hands dirty with the math, solving both parts of the problem, step by step. And finally, we'll zoom out and see what the solution really tells us about how things move.
Okay, so you know how it is. Before you can solve anything, you've got to really understand the question. So let's start there. Let's take a close look at the puzzle Irodov set up for us.
So the problem lays out this scenario with a particle that has this kind of unique thing going on. Its speed isn't just changing over time, it's changing based on its position. It's also giving us a starting line. At time 0, we're at position 0. Our mission is split into two parts. First, figure out velocity and acceleration as functions of time, and second, find the average velocity over a certain distance, s.
Okay, hold on. Before we jump into any equations, let's just try to take a picture of this in our heads. What does v equals alpha times the square root of x actually mean? Well, the particle starts at x equals 0. The square root of 0 is 0. So it starts from a dead stop. But as it moves forward, as x gets bigger, its velocity keeps going up. The farther it gets, the faster it goes. It's this weird link between where it is and how fast it's moving that we need to unravel.
All right, every physics problem needs a toolkit, right? And for this one, we're going back to the absolute fundamentals of kinematics, the core definitions that are built on calculus. Let's just do a quick refresh on the two big ideas that are going to unlock this whole thing.
Okay, tool number 1, velocity. We're not just talking about speed, we're talking about the instantaneous rate of change of position. And that calculus form, v equals dx over dt, that's the golden key. It connects the where with the when. This is our most important tool.
And tool number 2, of course, is acceleration. It's just the rate of change of velocity, written as w equals dv over dt. Once we figure out velocity in terms of time, this definition will hand us the acceleration on a silver platter. And believe it or not, with just these two powerful ideas, we're ready.
Okay, toolkits are ready. Let's get our hands dirty. It's time to solve the first part of the puzzle, finding the particle's velocity and acceleration as functions of time.
So here's the plan of attack for part A. It's actually a really logical flow. We'll start by building an equation using our definition of velocity. Then we'll do a bit of rearranging and integrate. We'll use the initial conditions to nail down our specific solution, which will give us position versus time. And from there, a couple of quick derivatives will give us everything we need.
So, first things first. We take the equation the problem gave us, v equals alpha root x, and we swap out v for what it really is, dx over dt. And boom, we have a differential equation. Now, how do you solve something like this? Well, there's this awesome calculus trick called separation of variables. All we do is get all the x stuff on one side and all the t stuff on the other. It's a simple move, but it lets us integrate both sides separately.
Okay, time to integrate. The integral of dx over the square root of x is 2 times the square root of x, and the integral of alpha t is just alpha t. But wait, don't forget that little plus c that always pops up with integrals. This is exactly why they gave us those initial conditions. The problem says when t is 0, x is 0. We plug those in, and what do we find? C has to be 0. Gone! It makes things so much cleaner. So with that pesky c out of the way, we have this nice, clean relationship, 2 root x equals alpha t. Now we just need to get x by itself. We square both sides, divide by 4, and there it is, our position as a function of time. And that right there, that's a huge milestone, because now we can just go back to our toolkit, differentiate x with respect to time, and we get our first answer, velocity as a function of time. And now for the big reveal. This is where it gets really cool. We take that velocity function we just found, we differentiate it one more time to find the acceleration, and check this out, the t just vanishes. We're left with a constant, alpha squared over 2. I mean, how cool is that? The motion started out looking all complex, depending on position, but it turns out it was just good old constant acceleration hiding in disguise. That is a major insight. All right, so we've cracked the first part of the code and found that hidden constant acceleration. We've got all the pieces we need to confidently move on to part B, finding the mean velocity while the particle travels those first s meters. So let's talk about mean velocity. What is it really?
It's just the total distance you've gone divided by the total time it took to get there. Simple as that. Since our particle is only moving one way, the distance is just s, so our only job here is to find the time it takes to travel that far. We'll call that time ts.
Our strategy here is super straightforward. Remember that position equation we worked so hard to get in part A? We're going to need that again. We'll use it to figure out the time it takes to get to position S. Then, we just plug that time into our mean velocity formula and simplify.
Okay, let's do it. We grab our position function and we just say, okay, when is x equal to s? From here, it's just a little bit of algebra. We multiply by 4, divide by alpha squared, take the square root, and we've got a perfect expression for the time it takes to travel any distance s. And here we are, the final step. We take our formula for mean velocity, and we plug in that expression for ts that we just found. We just need to clean this up a bit. The s on top divided by the square root of s on the bottom leaves us with a square root of s on top. And there it is, our final answer for part B. Done!
So, we've wrestled with the calculus, we've done the algebra, and now we can kind of step back and look at the whole picture. Let's pull all our results together and, more importantly, talk about what we've really learned here.
So let's put it all on the table. For part A, we found a velocity that grows in a straight line with time and a completely constant acceleration. For part B, we got the super tidy formula for the mean velocity. It's pretty amazing, right? We started with this kind of weird-looking relationship, v equals alpha root x, and we ended up with these beautifully simple answers.
So what's the big takeaway here? Well, this problem is a masterclass in turning physics into math. It shows how calculus isn't just a subject, it's the language of motion. It's also a great reminder that those initial conditions aren't just extra details, they're what pin down the one specific answer we need. But I think the coolest part, the real magic trick of this problem, is seeing how a strange-looking rule for velocity can secretly describe something as simple and familiar as constant acceleration.
And that discovery leads us to one last really interesting question. Since we found out the acceleration was constant, could we have just skipped all that integration and used that classic kinematics formula we all learned in high school? You know the one? Well, let's see, shall we? Our initial velocity v0 was 0. Our acceleration a we found was alpha squared over 2. If you plug that into the formula, you get x equals 1/2 times alpha squared over 2 times t squared, which is exactly the same formula for x of t that we got the long way. And what does that tell you? It just shows you how beautifully consistent physics is. The deep calculus definitions and the handy formulas, they're just different roads to the same truth.